Okay, so today we'll go with the Verilog. As we mentioned in earlier, that this is a circuit that we would like to design. Of course, I can give you like a description of that you have like to write, to use an inverter, you have to use an OR gate, you have to use an and this is the type of connection that you need to use. Okay, so you can just grab from the tools that you are working with, either Vivado or Quartz2 or any other tool that you are working with. You grab like the inverter, you grab this, you grab that, you do these connections, you find that this is the inputs and this is the outputs and so on. With a small or simple circuit like this is something easy that you can do. But what will be the case if you have something like that or even more complicated? It's so difficult just to work on that level and to begin to see like grab each component and make these connections and so on. Unfortunately, 20, 30 years ago, this is what usually the designer is doing. But then they thought like, let's simplify the things to the designers and begin to create a language. Because with this as an example, a description, I can describe it in English. Yes, I can describe in English. I would like a circuit to do this and this and that, and I would like this, the inputs, how many is the input that's available, how many is the outputs. I would like this to do that. I would like all whatever like I would like to describe. Or I can describe that we have an AND gate, and this AND gate has two inputs, and these two inputs is the output of this, the output of that, and so on. Like this. However, of course, this won't be like a scientific way to describe this stuff, correct? And that's why we will need what we called a hardware description language, or a computer readable textual language for describing the hardware circuit. So it will be hardware description language. Hardware description language, HDL. And this will basically describe the circuit in a way that the computer will understand. Popular language, VHDL, very high description language, which we will not cover in this course. However, if you know Verilog and the concepts of Verilog, then you can easily understand the VHDL, or the other way around. If you know VHDL, you can easily understand the Verilog. You can think of this like as a two language. If you know Java, it's easy like to get to the Python, or if you know C, of course it will be easy to get to any other language, and so on. There is also a system C. But our concern here will be this guy. So what we will learn in this part of the course will provide the knowledge in how to use the hardware description language to design and validate digital logic. It's exactly the example that I just showed you, but we'll see like how we can do that. But it's more complicated because our ultimate goal is to design a mini CPU over the FPGA. So it's not as simple as that, but we will begin with these kind of things. And then we'll move forward with more complicated and difficult stuff. But at the end, you will get the reward of getting the experience of a language like Verilog. You will learn also how to synthesize the HDL into hardware using the same tools that you might see in the industry. You will see the synthesis and the verification. You will see like how the design tools that's commonly used. You will see, like, as we will mention, how to write a test bench, how to think in hardware, and so on and so forth. So you will get a real experience of how things is going into industry. So what we will do will specify at a register transfer level, what we call it like RTL. You can go like from registers, combinational logic to registers. You can describe the whole system, or you can begin to describe just like these blocks and connect it together, as we will see in class. Okay, so let's spend some time just like with an overview of the descriptions phase. At the very beginning, you will have a specification. So what does that mean? Meaning that either the specification will come from a customer, or it will come from your manager in the company. We would like to design this and this and that. Correct? This is the specification. This is the very beginning. Then what you will do, begin like to have the plan, how I will design that, what exactly the environment that I will use, if I will go with the FPGA or if I will go with microcontroller or processor, whatever the thing is. And then if I decided to go with an FPGA, which is Field Programmable Gate Array, which the one that we will work heavily with in this semester, then which type of FPGA we will use, which company we will use, what will be the power consumption that we will approximately need, what will be the area that we will approximately need, and so on and so forth, because not all of the FPGAs have the same area. Some of the FPGA are small, some are very big, some are just middle, and so on and so forth. Not only that, even the frequency, it might have like some frequency restrictions. So what is so you, in this planning, you spend a lot of time in order to know what will be the next step. So assuming you know that, you have your design entry, you have this approximately like block diagram connections and so on, and then you will begin to design like what will be the functional test, like how I will test my design, what exactly I need to have in order to test my design, and so on and so forth. And then after you have something like that, you will go to the synthesis. So assuming you decide to go with the FPGA, of course you can, as we will see later on, that you can write a code, but unfortunately this code cannot be downloaded over the FPGA, because in our terms we call it non-synthesizable. You cannot synthesize, unfortunately, that code over the FPGA. It can't happen, and we'll see like some examples on that. It's not possible. Okay, so assuming that you passed the synthesis and everything went okay, you have to do a post-synthesis test. What does that mean? Meaning that after you get the possibility to download your design over the FPGA, you have to retest. Why? Because now it's like in the real environment, and you would like to have a real environment test. You might get like a simulation test. All of this will be in the simulation, but I mean just a simulation without synthesize. So this might not take, as an example, the delay of 1 or 2 or 3 of the components. It might not take exactly what will happen after downloading over the FPGA. But if you are doing like testing post the synthesis, you are taking approximately a lot of the environments that you will face when you download that over the FPGA. And then, of course, after that, you will go to manufacture and hardware validation, and then just like deployment and support. Of course, in our case, we will not manufacture, and unfortunately, we will not get the time to do a hardware validation. So, in just like a summary, the HDL, or hardware description language, this is just a text or textual description of digital logic, but it is not a programming language, and you have to remember that, especially for computer science major. It is not a programming language, as we will see. Because in our case, like, we will have modules and so on, but unfortunately, if you are like a computer science major, you always think as a function. I'm calling a function and so on in that way. It is similar, but not exactly the same, as we will see. Here, whatever like you write, at the end, it will be something there. There will be like a hardware that will be transferring whatever. There is a program that will transfer whatever you wrote to a hardware. There will be something there. It should be something. Whatever you describe, it will be at the end there inside the FPGA. And the task that the program will do is this transfer from your writing to the hardware, to the real hardware components. So I can give a description as an example, and that description with the language, with the Verilog language, it will be transferred to this AND and OR and inverter, that the simple example that I gave you. Okay? So this gives you an idea that at the end, whatever you describe will be a hardware. Correct? You will not choose exactly what is the hardware, which make the actually job simpler for you, but you have to put in your mind that this will happen. The program or the task of the program that you are using is to get whatever you are writing as a language to a hardware. And that's why it's called hardware description language. You will allow to get like the modeling and simulating the functional behavior and timing of digital hardware. There is also, as I mentioned, the synthesis tools that will take whatever you wrote, it's HDL description, and will generate the technology-specific netlist, or in another way, the real hardware representation of whatever you are defining. As I mentioned, there is like a Verilog and VHDL. The Verilog will be based on C, so hopefully it will be also a little bit easier for you to understand if you are familiar with a software language. The VHDL, it's again very high speed, also integrated circuit hardware description language, or very high level description language, and this is developed by the US Department of Defense, and also both are IEEE standard. So why use the high hardware description language? Again, more and more transistors can fit on the chip, because now you can have like a very large design by that description. If you don't have that, unfortunately, you will spend like hours and hours and hours just like begin to build. And unfortunately, it will not be also portable. In another sense, if you have a design without the language, if you're just like creating the blocks, and if you are creating the blocks in one of the tools, unfortunately, the migration to another tool will be so difficult because they might not have exactly the same library. In another sense, what does it mean, the same library? Just to give you an example, that you have in your design an AND that has 3 inputs, but maybe the other library only have ANDs that have 2 inputs. And then when your design need to be transferred there, then you need to use 2 ANDs instead of just 1 AND with 3 inputs, or 1 AND with 4 inputs, and so on. However, if you wrote your design in a Verilog or a VHDL, it will be easily transferable. So you can just like get your code, go to that tool, and then run it over like an Altera, and then take exactly the same code, go to Xilinx, which is Vivado in your case, and run it. So it will be transferable, easily transferable. Okay? Yes, so of course, also like many designs need to go to production quickly. In another sense, you are just abstract large hardware designs. You will describe what you need the hardware exactly to do. And then the tool then will design the hardware for you. So even though it is as easy as that, we'll get like a lot of complaints of debugging and so on and so forth. But this will be the experience that you will get in this class. Again, simplified and faster design process. You will explore large solution space and so on and so forth. Less time spent through the debugging the design. Of course, much less than if you are building all the blocks by yourself. It's so difficult. And as I mentioned, you can reuse the design to target different technologies. So you can get like to Altera, you can get to Xilinx, you can get to Actel, you can get to any other FPGA and tools. There is no problem. So it's highly portable, as we mentioned, self-documenting, describe multiple levels of abstraction, and then you might provide the description in 3 ways: structural, or RTL, or behavioral. In our case, we will concentrate more in the third option, and we'll know why. Again, I would like to emphasize might look like a software, but unfortunately they are not. So they are not a program and can't run on anything, meaning it might be not synthesizable. It can be good like in the simulation, but unfortunately after you have like the synthesis, it won't work. I will give examples for that. So as I mentioned here, some special HDL code can be used more like a software, but this can be only for simulation purposes, not for synthesis. In another sense, you can think of a test bench that can something that you can write for simulation purposes. Yes, because basically you will use this for simulation purposes. So the test bench, you don't have to have your test bench synthesizable, meaning that the code that you will write in a test bench, you don't need to think about like if this can be downloaded over the hardware or not, because you will not download that over the hardware. What you will download over the hardware is your design, but the test bench will be in a process before the download. The hardware verification will be like after the downloading, but this does not have like anything with the test bench that will be written in order to test the design of the FPGA. In the hardware, you will design the total or the whole design. Of course, you will have like an oscilloscope, you might have a function generator, you might create like some of the signals that you will create from the computer. You can send it through the serial or USB port, and then you read back and so on. This is another thing. But I'm speaking about the test bench that you will write in Verilog. The test bench or the language or the code that you will write in Verilog does not have to be downloadable over the FPGA. We will go over that a lot soon. So synthesizable code can be converted into a real hardware, which will be bound by the same limitations as a hardware and can both be simulated and synthesized. Fortunately, non-synthesizable code, this means that this is just will be for the simulation and can't represent the behaviors that are too difficult or too expensive to be created in the real hardware. We'll see an examples for that. Example for a synthesizable, if I have like a 3-input AND gate. Non-synthesizable, I can't write a Verilog code that I would like to download over the FPGA, that a 3-input AND gate that has a delay of 5 nanoseconds on weekdays and 10 nanoseconds on weekends. If I will write that, unfortunately, it can't be described in the hardware. And this is what I meant with non-synthesizable. Not be able to do that. It can't be transferred to a hardware. Yes, you can write software code that describes something like that, but unfortunately, you will not be able to do that over the hardware or over the FPGA. Okay? So, of course, unfortunately, it's not always so obvious that you will determine if it is synthesizable or not, and this is something that will need more like toward like experience and so on and so forth. You might face like some issues at the very beginning, but later on you will get the experience to know like, no, this is not synthesizable, I have to remove it, and so on, so forth. So this will rely more on your knowledge and your hardware capabilities and experience. So this is like a hardware building blocks, transistors, or using multiple transistors. At the end, you will have the gates, or you might have like a multiple gates. So as an example, you might have in your tool a library that you can grab a component like that. And this is what I mentioned earlier, that you might have, as an example, in Quartz 2, a component like that, you can grab it, okay? If you were like to design by blocks. But unfortunately, when you go to Vivado, and you would like to transfer your design, Vivado will not be able to transfer this because unfortunately it's not in their library. And they will not be able to do that automatically to change it with whatever the library that they have. But if it is written in Verilog or VHDL, it will be like a smooth transfer between the tools as we mentioned. So with the FPGA, the field programmable gate array, and by the way, when they actually invent this was a breakthrough. Because the problem that designers had earlier. So this was, as I mentioned, a breakthrough, because earlier you have to design something. Okay, that's fine. Go ahead and spend all the time till you have your design. But then test it. Unfortunately, there is a lot of errors, but you already spend a lot of time in order to bring the components, to connect it together, and so on and so forth. Money, time, and you may even do something wrong in your design in a way that as soon as you switch on, the whole circuit will break and the whole design will burn. So you lost all of this money and the time. Correct? It's not even like that. So people who worked in the VLSI, when they create the chips, they have also, like, again, all the way with the design, with the simulation, everything like in the simulation looks okay, and then they send their design to the warehouse. And the warehouse will transfer that design to the chip, the wafer. If you open the IC, you will get at the end like inside the wafer. And with this wafer, actually, there is millions of gates and transistors and so on. But the problem that if there is only one transistor or one gate that is wrong, the whole design will be wrong. And you already paid like thousands of dollars to the warehouse in order to download or in order to design whatever you have sent to them into the wafer. You can't go back. You can't say like, hey, no, give it that back. I'm sorry, I sent you the wrong design. I would like to send you now the new design. Please re-download it with the same price. Unfortunately, you have to pay again. And of course, if you were like the CEO of a company and you have like employees that you will keep doing the same mistake, and each time with this mistake you are paying like thousands of dollars, what will happen at the end? And that's why the invention of the FPGA was like extremely useful for companies and also for designers. Because now it's like multiple of times that you can download your design over the same exactly hardware without paying each time a new fees. It's just like one time you buy this FPGA and then you keep reuse it. So it's programmable. That's why it's called programmable. Yeah, field programmable gate array. So you can, every time you reprogram that particular hardware. And that's why it was like a breakthrough at the time. Because at the end, you can think of this FPGA like that, and you have like all of these, and then at the end, you can do like, yes, I would like to do like, as an example, these connections. In this, I would like to do that connection. I would like to do that connection, and so on and so forth, and then run to have the circuit. And then when you are re-downloaded, you are just removing whatever the connection that you had earlier, and you have a new connection, and so on and so forth. You might have it like a design like that, or whatever. If you go all the way till the transistor, you will have like something like that. So just like as a review for the finite state machine, when we begin like to do or would like to design, so it will determine a finite automata. It can have like a combination and logic and flip-flops. And this will be often used to generate control signals, and it will react to inputs and so on and so forth. So you can have examples for finite state machines, counter, vending machine, traffic light controller, phone dialing. All of this is just an example of finite state machine. There is a Moore and Mealy finite state machine. Can anyone remind me what will be the difference between a Mealy and Moore? Mealy and Moore finite state machine? So the Mealy machine will depend on the state and the input, but the Moore machine will only depend on the state. Just as an example, so if you are taking like this course, okay, and this course is a prerequisite for a next course, transition from this course to the next course, given that this is the prerequisite for the other one, is it a Mealy or Moore machine? It is a Mealy machine. Why? Because it does not only depend on the state that you have it right now. Yes? In order to go to the next state, you will be able to go to the next state if you are in this state and you pass the course, given the input, yes? Correct? So when you are in this state and you have the input of passing, then you will be able to go to the next state. But if you were, as an example, to be like in a train or bus stop or something like that, if you are in this bus stop, you know for sure that you will be next in that bus stop, unless there is any other like traffics or road work, whatever the problems that we have here right now. But I'm just speaking about normal situation. This is a what? A Moore machine. So yeah, so here you will have like the next state logic. If you have like a certain input and you was in a certain state, then you will go to that particular place and so on. So if you are in this current state and you have a certain input, then you can go to this next logic and so on and so forth. So here just describe whatever we mentioned, but one more thing I would like to highlight, that here the outputs are always synchronous, but in the Mealy it can be asynchronous or synchronous. Do you know what is the difference between synchronous and asynchronous? Anyone know the difference? Yes? Yeah, so basically synchronous will be controlled by a clock. But asynchronous is just like can be in any time. Whatever you will have your output, just like show it to me. Yes? But if I'm saying like with a clock, just like for the real life, as an example, I'm giving you like a problem to solve, and I will say like I will ask each minute if you did finish or not. And you have this possibility only to answer at that time. If you finish it in between, I will not hear to whatever your answer. You blocked, just like you don't have your microphone. But at that time, when I said like, hey, at that the beginning of the minute, did you finish? At that only time you can say yes or no. In between you cannot. This is synchronous, yes? Meaning that the output is just synchronized to another thing. We might say that this is a clock, yes, in our case. But I'm just trying to make an analogy, yes? Because the problem in our brains that we do understand examples like that, but we don't understand when we are beginning just to speak about abstracts and just like equations and so on and so forth. So asynchronous in that example, when you said like as soon as you finish, you can say like, hey, I finished. This is asynchronous. You don't have to stick with another time or another clock. Whenever you finish, you say like, hey, I finished. In the previous example, when you say like, I finished, while I'm not in the click of saying like, did you finish or not, I don't care. I will not take that into consideration. Fine? So with this HDL design flow, at the very beginning, of course, you will write your code, and then you will compile it and see like if you have any errors and so on and so forth, and then you will begin to do like some simulation, and after that simulation you can do synthesis, or you can just don't do the simulation and then do the synthesis and then do the simulation after the synthesis. Of course, this will be a non-synthesizable code. You can create a test bench to test your design, and then you will simulate using your test bench. And then you can have like a code synthesizable with the synthesis tool, and the tool will convert your code to a real hardware elements, meaning gates and cells, lookup tables, etc. LUT, lookup tables. Then you will simulate this netlist with your test bench. As I mentioned, you can simulate 2 times, or you can just simulate 1 time after the synthesis. It depends on like how much is your experience. And then what is the netlist is basically a physical design description. Concentrate on the connectivity of the components. With the variables, you have like a net, you have a net and variables, and the net will be represent a physical wire. We'll go over that in details, I think, today. It will describe structure connectivity, it will assign to continuous assignment statements, and so on and so forth. With the variables, will be used in behavior procedural blocks, will represent synchronous registers and combinational logic. I'm going fast now because this will be described shortly, heavily actually. With the Verilog operator, of course, you will be familiar with all of these things, the arithmetic that you will need, plus, minus, multiplication, division, power, and so on, with this logical, bitwise, or using the replicate or concatenate. We will learn all of these kind of things. Also the shift, how you can do the shift operations, and so on and so forth. We'll be familiar with that. Okay, so this is just the very beginning of how to write just like a simple syntax in the Verilog. Okay, so assuming that I have a certain output, as an example, or a certain signal, let's say that way, a certain signal that I would like to assign a value to that particular signal. So I would like to say like assign to that particular signal x a certain value. We'll understand now in a minute what that value is. But just I would like to assign a value. Before I can assign a value to this, I have to define x as something. Yes? In that case, if I'm using an assign, I have to define it as wire. So I will define it as wire x, semicolon, before I use the assign state. Okay? If, as an example, you did not define that and you wrote this line, it will give you an error. And then you will spend like a lot of emails going back and forth, why I'm getting here an error, I wrote my code correctly, and unfortunately, the last thing that you will think about that you are wrong. So you might say like we are wrong, you might say like the tool has a problem, the computer has a problem. The last thing that you might think of that you unfortunately have the problem, or your code has the error. And most of the cases, this is the situation, that your code has an error. Okay. So this is equal 1, bit 1. We'll understand in a second why it is that, but just like what I would like to say here right now, just if you assign a variable, you have to define it as wire x at this moment. So assuming I have an x like that as a signal output, and I have inputs A and B and C, and I would like to say like, hey, x is A or B or C, as that x is equal to A or B or C, so I will use assign x, but I have to define it, again, as I mentioned earlier, you have to define x as a wire. Okay? The same exactly will happen if I would like it to do A and B and C. Assign x equal to A and B and C. I have to define wire x in advance. The same apply if I would like it to have as an AND, which is not the ANDs, yes? Again, the same. This is how we will write it in Verilog, and this is what we need to assign to x before we begin to, what we need to define x before we assign values for x. There is also something called module, and this module will be the basic building block in Verilog, and this can be interconnected to describe the structure of your design. the modules will start with the module and will end with an end module. And I think you have already seen that in a previous course. You can also declare input, output, or input-output bi-directional, meaning that if you have a block like that, you might have inputs, you might have outputs, but also you might have input-output, that you have the output and can go to the input like that, a feedback, yes? You have to have a design, you have to have a description for that, and this is in-out, but this is rarely we will use it, yes? Very seldom that we will use something like that. If I would like to define as just one of these input, I'll say like, hey, input Cn. This is the input, C input. But if I have a range from the most significant bit to the least significant bit, I will write that in that way, 7:0 or 0:4, whatever you would like. So this means that your output is how many signals? In this case, 8 signals. Your input is how many signals in this case? 5 signals, yes? You can think of this like as a bus or something like that has many inputs or many outputs together. Okay, so let's take an example. You have this design, and this module is called circuit, and that's why I define here module and I give the name that is here. And since I have the module here, I have the end module here. I have A and B and C and X and Y and Z. Define the input A, input B, input C, output X, Y, and Z. And then I will assign X and Y and Z. I have assigned X equal to this, assign Y equal to that, assign Z equal to that. The question is, there is no wire here. I did not define X and Y and Z as a wire, as I just mentioned. Am I deceiving you or what? The issue that if you did not define that variables as a wire in advance, but you define it as an output, that's fine. That should be fine. You have to have like a description to that signal before you begin to assign it. If it is in between the design, then you will call it wire. Meaning that you will have a design here, you will have a design here, this is the outputs, this is the inputs, but you have something in between, which you can't define as an input and you can't define it as an output. However, at a certain time, you would like to assign a certain value. At this situation, this will be a wire. But since I have this as an output, so I can just call them as an output. Because this will be like a real output to the FPGA. They will be connected to one of the pins of the FPGA, and we will define it as an output. Okay? Another example, module F adder, full adder. You have input A, input B, input like that, output, output. And then in between, I will define some wires, C1, C2, C3, which is the carriers. Yes, carry on, 1 and 2 and 3. And of course, I'm expecting this will be in between. That's why I have defined them as a wire. And then I will assign the sum output, that is A XOR B XOR C input. I will define the assign C1 as A and Cn, and so on and so forth. And then the C output will be assigned like that. Of course, in the quiz or in the exam, if I would like you to write a code for a full adder, I should give you the equation. I'm not expecting that you will remember these kind of things. I'm not expecting that you will remember that. Okay, I should give you like the equation that you need to use. But your job will be like transfer that equation to the syntax, the correct syntax. Okay? So here just like shows also inputs and outputs, and it does show that you might have also something called H, which is input and output. And that's why it is defined as an in-out. So at the end, the module instances, you will have it a wiring up like that. You can think of this as an example at the FPGA. It is not the case, of course, but just like would like to make things like much more easier for you to understand. And you can think of these as some of the blocks that you will build. Here it calls like resistors, here is whatever the chip, oscillator, whatever, and at the end you have here a certain wires, yes? To connect between all of these things, and that's why that we will do. We will have like blocks with inputs and outputs, yes? And then we will have in between some wires that's connecting some of the outputs of some of the chips or the components to another inputs, yes? Which they have here as a wires. They already appear here as a wires, okay? So module instances, or another way how to instantiate a module. Assuming that you have this AND gate, and in your design you have two of these exactly AND gates similar to each other. Do I have in my design to write that I have this AND gate and then another AND gate, and I assume I have millions of these? I have every time to write in my code that I have to repeat the codes millions of times? Does not make sense, correct? I have to define it only one time, and then I will instantiate. In another sense, I will call it. I already defined to you what is AND. So when I told you AND, you know what is the function of AND. What I need to give you only what with the inputs and outputs. And you know what is the function, because I already defined it to you. And what we will learn from this slide is how to write something like that. First of all, you know that this AND will be defined here as a module. I will call it AND2. AND2 means just give an indication that has two inputs. And this, it does have two inputs, input I0, input I1. If you look at this, if I zoom into that one, if you zoom here, you can see like this is I0, I1, correct? Yes, so I am describing this AND. This AND does have like an input I0, input I1, input I0, input I1, output O. And then this O, a sign O, is basically the first input ANDed with the second input, and then end the module. Okay? Then I will go to write now my design. My design will be module circuit. This is called circuit. And this circuit has input A and B and C and output X. Input A and B and C and output X. And then it has a single in between called temp. And we said that if it is in between, I can't call it an input and I can't call it an output. Then I have to call it as a wire. In this case. And this is what I will define, wire temp. And then now I have two ANDs, 1 and 2. What I should do is what? Instantiate this, means call it and call this. And what I should do is I should say that this I0 is connected to something called temp. This I1 is connected to something C. And this guy I will call it AND2, but A1. And I will connect I0 to temp. I will connect I1 to C, I will connect O to X as I already explained here. O to X, I1 to C, I0 to temp. How about that guy? That guy, the I0 is connected to A, the I0 is connected to A, the I1 is connected to B, the I1 is connected to B, the O is connected to temp, the O is connected to temp. And this is the syntax. And then, if I have it like that, it will understand that this is that circuit. However, I don't have to write each time what is exactly the purpose of AND2, so I don't have to write this millions of times here. I just define it one time, and then I began to instantiate that. Okay, so as an example, a feature like that is not available in VHDL. Okay? So here is just describe whatever I just mentioned. So you can have your code described like in what's called like a structure, or another word for the circuit. So you have to define this, you have to define this, you have to define this, and then to begin to connect each of these together, which as an example to the previous slide, but just like we have like more components now. And what we will learn from the next slide is how to do exactly the same things but with another way of syntax. And in the quiz or in the exam you can use any of them. However, you have to be familiar with both, because I might use any of them in the exam and ask you to go the other way. So I might give you one of the syntax and ask you draw the block diagram or draw how it looks like. Correct? So you have to be familiar with any of the syntax that I will share with you here in the slide. So if you look closely here, this is, we have an inverter, we have an OR, we have an AND. So we have to define all of these. So we have module. By the way, this E is it's just like a typo. Yes? But it should be module. E should be with this. So module env, and module env has the inputs X, output F. And you can write it that way, X comma F, and this is the other syntax. Module OR, which is this one, OR 2, inputs and outputs, define that, and again another module which is AND, inputs and outputs and so on, and then end module. So now you have defined all of these three components that you have. Then the next step is what? Just like connecting all of these components together. And this is what we call like structure description. So what we will do, you can say like the circuits or door opener, since I call it here door opener. So the module here is door opener, has C and H and P, so on. And then the inputs is like that, C and H and P, because the input is C and H and P. The output is F, the output is F. I'm defining the big circuit. And then I will begin to have like wires, since I have here a wire N1 and another wire N2. I will define it here as a wire N1, wire N2. And then I will instantiate the env, I will instantiate the OR, I will instantiate the AND. And just like try to look closely here. Again, maybe we need to zoom in. So as you can see with this env, so we define the env here as X and F, and this X, which is the input X, because this is X and this is F. We are saying like this X will be connected to C, because this is the first to the first, and this F will be connected to N1, so the second to the second, and so on. So this is another way of defining the same exactly thing with another sentence. Okay? And so on and so forth with the AND and the OR, you can do it yourself. Also, you can concatenate vectors. So if I have module concatenate, and this concatenate will have like some outputs and inputs. As an example, input 2 to 0 A, input 1 to 0 B, and the input also C. You can write all of them, by the way, in the same line. You can write here input this, and then comma this, and then comma this, and so on, and at the end you will put the semicolon. It's another option that you can do. And then the output 7 to 0, and this is defined as an output, meaning that the A is basically 3 signals, yes? Correct? A0, A0, A1, A2, because it's 2 to 0. So I have A0, A1, A2, correct? This guy, B0, 1 to 0, means I have B0 and B1, and so on. And I would like to assign an output that will be with this shape. This means that I am concatenating to that outputs some of the inputs. How I can do that? I'm saying that, hey, the first one here, is A of 2, meaning that the first connection here will be A2, as you can see here. Then D, then D, then C, and I know from here that C is defined as 1 to 0, so this means that I have C0 and I have C1. Then B I know that it is again 1 to 0, so I know that I have B0 and I have B1. And then A, but 1 to 0, so I am taking part of the A. I'm telling you, like, don't take all A, just take A0 and A1. Don't take A0 and A1 and A2, just take A0 and A1, and you write it that way, and that's why it is A0, A1 like that. Okay? So representation of numbers, I told you earlier, but I will tell you, like, if we have like one bit 1, if you remember the x, assign x. So here, the size, the base, the number. The first thing that I will give to you here is the size. The second thing is the base. What is the base? And then the number. So if you recall the x, I said like x1, b1. Do you remember that? That slide, x equal to 1, b1 means size is 1. B is binary. 1 is the value. What is the size? This is what you just like said, that why it is 2 or something like that. It's here you just give the size. Say like, hey, this is a bus of 8. Yes, the size is 8. Or you have to write this in 8 bits. In another way, you have to write that in 8 bits. What is the value that you need to write? 17. How I can decode that 17? It is decimal. Or 17, let's call it that way, 17, because it might not be 17 exactly if I'm using another representation, yes? And so on and so forth. So let's take some examples for something like, anyway, this is just like show you that we can have like a decimal, hex, octal, or binary. By default, the size is 32 bits. But why I have to use like 32 bits while I just need 2 bits? That's why it's very recommended to write like what is the size. Otherwise, you are keeping like take resources from the FPGA while you don't need that. Then at the end, you might face troubles of like your design is not, unfortunately, the size of the FPGA is not enough for your design. Your design is much bigger than the FPGA. And you don't want to go to that issues. Example, for D3. Meaning decimal, the number of 3. But I would like to write this 3 in 4 digits. That's why it is like that. This 8HA. So I have the value A. It is in hexadecimal, but it will be written in 8 bits. Like that. I have 111, but this is binary and need to be written in 5 bits. But since this is binary, so I read it just as a 111. But since it is written in 5 bits, so I have to add 2 zeros. Agree? Yes? It is 3111. It's 7 at the end, yes, but it's 111. And then I have to add 2 zeros because this is need to be written in 5 bits. So here the two basic categories, the nets and reg variables, registers, and we'll speak more about that later on. So we have also wires and tri. And tri-state is basically same functionality as the wires, but this will be used as a tri-state buses. But we will also very seldom use that tri-state. We will either use a register, reg, or a wire, as we will see in the examples. Here you can read this for your own. Then how to write like or build a testing module. So assuming you will create a circuit, then you will develop a separate tester module, and then you will write your test bench. How we can do that? Let's take as an example of how to do that. So this is your circuit. This is your tester, and this connection between your tester and the circuits, I will say that this is the test bench. Let's take that example. You have your circuit. Here you need, you already designed, and you would like to test that. And then you have that code. But let's concentrate on some of the issues here before we move forward.
At the very beginning, the code, you have like a time scale, 1 nanosecond / 1 picoseconds. What does that mean? This 1 nanoseconds means that the times that you will use will be in nanoseconds. So I'm just like at the very beginning, we agreed any time that I will write in the test bench will be in nanoseconds. If I write any other things, it will be with that particular units. But now if it is nanoseconds, it is nanoseconds. / 1 picoseconds. What does it mean, 1 picoseconds? Meaning that this will be the precision. In another sense, if you have a clock, as an example, or a watch like this, which have like the precision like that, the precision in this case will be what? 1 second, yes? Less than 1 second, I can't tell you. It's not a stopwatch. Yes, the precision here is 1 second. So this gives you an indication that if you have any movement that is less than 1 second, unfortunately, I will not be able to record it. Yes, if it is 0.5 seconds, I will tell you it is 1 second. Or 0 seconds. It depends on whatever the precision, or my eye will see it while you are asking me, correct? Here exactly the same. The precision is 1 picoseconds. So any change in time that is less than 1 picoseconds, the problem I will not be able to recognize. I will only be able to recognize anything that is 1 picoseconds or more, because my precision is 1 picoseconds. Less than 1 picoseconds, I won't be able to see. I will just refer that to the one before. Yes. So if it is 1.2, I will see it as a 1. 1.6, I will see it as a 1. 1.6 picoseconds. In another sense, if I'm telling you like, hey, your clock is raised now, and after 1.6 picoseconds, it is off. Nothing. I don't know. It's just still rise and off at the same time, because I can't count anything that is less than 1 picosecond. So in that sense, again, this is the module circuit. This circuit is defined here. And we already defined this with the AND gate, instantiate that. This was our design that I have covered earlier in one of the slides. Then, how I can write my tester. My tester is saying here that at time 0, initialize x equal to 0, y equal to z equal to 0. And then after 10 times units, in our case, it's nanoseconds. So after 10 nanoseconds, please set x to 1. After 20 time units, which after 20 nanoseconds, set y to 1, and so on and so forth, 30, 40, and 50, and so on. So how we can write a test bench or tester that will do that? Here it is. Module tester. Of course, this has outputs. Output, x and y and z, but we have to define them also as a register. Output register, and so on. And then we initialize, begin. At the very beginning, I'm telling you that x equal y equal z equal 0, x equals 0, y equals 0, z equals 0. And then after 10 nanoseconds, set x to 1. After means here the pound sign. After 10 nanoseconds, please set x to 1. After 20 nanoseconds, set y to 1. So after 20, yes? But I have already left 10. So I have to add 10, because this is 20 is absolute from the very beginning, yes? But now I already passed 10, so I need another 10. That's why here another 10. And then after 30, I already have 2 20s, so I need another 10, and so on and so forth. I'm just representing this into the Verilog, and at the end, after this 50, which is after another 10, finish. Is this clear? The next step is how I can connect this guy to this guy, because I have this now, I have this now. This is tester. I wrote here time scale 1 nanosecond / 1 picoseconds, meaning that the time is in nano and the precision is in pico. The next step is how to connect both. How to connect both. This is exactly the same things as we took in instantiating, or how I can instantiate a component. So I will build a big thing that's called test bench with the module test bench. With this module, I will call that, and I will call that, and then I will connect them together through these wires. So I will call circuits, I will call test, and I will call some wires here. these wires is, as an example, LMNO, as an example. And I will say like, hey, input A connect to L, assuming that this is maybe L, this is maybe M, this is N. So I say like, hey, input A connect to L, input B connect to M, input C connect to N, and so on and so forth. The same thing with the tester. Please, if you have here X and Y and Z, the X will connect to L, the X is connect to L, the Y is connect to M, the Y is connect to M, the Z is connect to N, the Z is connect to N, and then initial, begin, monitor please these values. And after monitoring these values, meaning that it will show up like as a print, assuming like as a print. Again, since this is a tester, it doesn't have to be synthesizable, and that's why I have after 10 nanoseconds, after 20 nanoseconds, and so on and so forth. But if I were to design something like that and would like to synthesize over the FPGA, unfortunately it is not possible. But since this is a tester, which will happen only in the simulation, I can write whatever I would like. Thank you, and have a great weekend.